times probably of R given Q. But they tell me that they're independent. So I can rewrite this as probably of Q times probably of R. Bam. I know this value, right? 0.1. I know this value times this I can solve. Because as long as you got one thing I don't know left, algebra steps in and says, I got you. Like, why would you help me, algebra? I hate you. And algebra's like, because I know. No, algebra, I care about you. You can't. Is that all right by itself? Okay. So again, what are some major general things you can take away? Write a formula for what they ask me, or if they ask me something that has no formula, write a formula for something they tell me. Don't skip a step where I tell you something important that actually has to deal with what these formulas change into. Mutual exclusive, independent. Write down immediately what that means, and then you can plug them in the formula in the right place. Okay, maybe. So statistics is the merger of algebraic kind of ideas with concepts. And that is sometimes considered gross. It is actually beautiful. All right, so let me get into some new stuff. So this is the start of chapter 4? Yeah, we're about to get into chapter 4. Yep. Yeah. Because we're crazy. All right. Yeah. So like I very often do, I'm going to go through a simple example problem that will explain why the processes we use work. What I'm going to do right now, you're never going to do. So why am I doing it? To explain the idea. Because what's most important, stats? The idea. Shit. All right, but I always get somebody like, why would I ever do it? Like, well, don't. This is just explanation of why things work. What we're doing is this. We're going to do this several different times. What are like the two most important things you can calculate from data that will quickly summarize that data? I love that question. What if we calculated over and over and over again the two most important little things that if I tell you those two numbers, you got a feel for what the data looks like? The mean? The mean and the better than the range. How spread out the data is. So all right. So those two. Now listen. Those two numbers, they tell me where the middle of the data is and how spread out it is. And I know we live in California, we don't get hurricanes, but I love this thing about there's a middle. There's where the hurricane is, with where I think it's going to go, and then there's the standard deviation of where I think it's going to go. You guys have all seen those maps, right? Where they got the cone of uncertainty. It's a beautiful representation of standard deviation. As it goes further along, I'm less and less sure, so it gets wider and wider, right? So if I just know the average and the spread, that tells me a lot. Just with two numbers. So I can have 18 billion data points, and I calculate the mean, just two numbers, mean and standard deviation, and I got a really good feel for all of them. You don't have to show me all 18 billion, please dear God. Just tell me two numbers, the middle and the spread. Okay, maybe. All right. So we're going to have several situations this semester where they give us data in a different way. Every time they give me data in a different way, we're going to, because we're smart, we're like, shit, I don't want to keep doing all this long-ass stuff. Maybe there's a shortcut to figure out those two numbers. If it's given to me this way, maybe there's a shortcut. If it's given to me this way, maybe there's a shortcut, right? So that's what we're going to work on right now. So here's the way they would have given me some data before. Let's see. Let's do that. And then, how many is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. Yeah. All right. So this would have been like a typical problem way back in chapter 2, like way back. And I asked you to find the mean and the standard deviation, right? Yes. Okay. But, so if I'm going to calculate, I'm going to say this is a population. Yep. So if I go to calculate the mean, how would I do that? Nothing, no tricks here. Just how do I calculate the mean? I would add them all up. Yes. But can I be smart about it? I can say there's 2 1s. Are you guys with me? 2 1s and 4 2s and 1 3 and 3 4s divided by 10. Okay, guys. So again, nothing amazing there, and I'm not doing any tricks by doing this shit. It's just an easier way to add 2 up 4 times than 4 times. All right, so this way is the old way. For a list like this, the old way is quicker. Yay! But I'm going to show you a different way to do this, so then when I get more disgusting data, the new way will be a shit ton quicker. Shit ton is an official measure. So the old way, what would we have gotten? We got to get the same number both ways. So what do I get this way? I would get 2 plus 8 is 10, 13, 25? Did I get that right? Nobody's going to help me. All right, 25 out of 10, which is 2.5. Yes. Yes, yes. Ooh, that's amazing, Jeff. All right. What's the other way I can look at this? Let me say this one more time. If I gave you this list, dear God, do it this way. This new way, I want to show you why it works, and then I'll show you where we're going to use it when it's something that's much more disgusting than this. This is easy. 10 numbers, who gives a shit? So watch this. Can't I say, wouldn't this be 2 tenths times 1? Plus 4 tenths times 2? And so forth? Right. Some of you guys are already like, why would I ever? Again, what did I just say? Definitely in this problem, I would do it this way. And why does this make sense? What percentage of the numbers are 1s? 20%. 20% are 1s, 40% are 2s. Okay, I like it. And then what do I get? 2 tenths plus 8 tenths plus 3 tenths plus 12 tenths. I get something, 25. I get the same number. That's amazing. Of course, because mathematically we did the same thing. So we're just amazing. Okay, stay with me. So, let me take this away. So when we would use this way is when they give me data like this. That represents that, right? 20% are 1s, 40% are 2s, 10% are 3s, 30% are 4s. Is that cool? So if I reached into this hat, what's the probability I would pick out a 4?
20%.
It's probably I'd pick out a 4. Do this. 30% chance because just 30% of them are 4s, right? You with me? So this isn't just a probability, percentage, this is a probability. So being remarkably creative, statisticians said, let's call this a probability distribution. So it's a lot like a relative frequency distribution, but now we say these mean probabilities. So remarkably enough, we say, let's call it probability distribution. All right. Now, notice what we did mathematically. What was this coming from? That was 2/10 times 1. These multiplied, and then these multiplied, and then these multiplied. Right? So wouldn't that be all the x's times each p of x? Isn't that what we just did over there?
Yeah.
And why does this make sense? Because 20% of the data is 1, so it should be 20% of the mean. I multiply each data value by its weight. And isn't that how you calculate an average? If the tests are 50% and you have an 80 test average, it'd be 50% of 80 plus 25% of your quiz average plus maybe. Have you guys ever done that? No? You just sit back and take whatever number they give you? Okay. So let's see. Multiply across 0.2, 0.8, 0.3, 1.2, and when you add those up, 2.5. See the little symbol I used? Why does that make sense? Because how did I get 2.5? By adding those. That's what add those, and I get this. So when they give me an x, p of x situation, what's the formula for the mean? The sum of x, p of x. Now let me see if I can sneak this in right now. If I had these numbers in a hat, and you picked a number out and put it back in, you picked another number out, you put it back in, you picked another number out and you put it back in, and I took an average of all that, you would expect over time the average you get should equal the mean. That's what the average should mean, right? The average of all the picks you took should get closer and closer to what the real mean is. So the number I expect to get when I average up all the times I do this is the mean. So that's why the mean is called expected value. And look at this shit. How do you spell expected? E-X-P other stuff, right? Oh, yeah. This is too awesome to believe. So another name for the mean, there goes, oh man, I'm like, Bernie Sanders. Only 1% don't know how to do this. Right. Expected value is another name for the mean. And that's too nice that the freaking formula has the letters E, X, P. We know that's not E, but screw it. It looks like an E. Okay, maybe. To me, that's just always kind of neat. But you have your stuff, Jeff. Quick. Okay. We still got to discuss. So that's one of the numbers, right? That's figuring out the mean. So we'll do a problem in a minute that'll show you why we want these formulas, because I can give you something that's much more disgusting than what this was. So I want to work with these nice numbers for a moment now, and let's figure out what the standard deviation is. Oh, real quick, by the way, this is kind of neat too. What was the formula for the mean before? And this it's not a new formula, it's just the formula we use repackaged if they give it to me like this. Because to be honest, these two formulas are the same. And that's where some of you guys go, you alright, Jeff? You should take your meds this morning. What's on the bottom of a probability? Any probability, what's always on the bottom? Total number of things. And what letter do we use for the total number of things? Alright, so N is still on the bottom of that shit. These are the same formula. Oh, yeah, that's the reason. No, it's exactly the truth. Right, so the main thing that's different between these two, oops, Jeff, I left that some in there. Somebody should have been yelling at me. The main difference between these two is, where's the over N? Well, it's in there. Like ragu, it's in there, it's underneath the P, it's a part of that. So they are the same freaking formula. Of course they are. Because how did we develop this formula? We started with that formula. So of course they're the same, it's just it looks different if they give it to me like this. Okay, I'll stop. So somebody help me out. All right. I'm going to write some stuff here because we're not going to do it this way. So here's the xp of x, right? All right, and that column would give me the mean if I add them all up. Now, how did we used to calculate standard deviation? We'd have to make a column of x minus what? What was the standard deviation before? I'm using these symbols because I said it was a population, right? That's the formula. You guys with me? Now get the moment, math boy. We're with you. So, technically, I'd have to make, and do you see how, in this example, now this is kind of bad the way I did this, but anyway, in general, I can't just add these numbers up and divide by 4 to get the average, because there's more 2s than there are 1s, and so forth, right? So how do I get the average? I multiply the x times the weight. So, normally I would make a column of this shit here, right? And then throw it in, but there's weights now. So I'd actually have to have each of these multiplied by the weight. So if I take the values multiplied by the weight and then add those up to get the average, I'd have to take the deviations multiplied by the weight. Because what percentage would be, so if I put the same percentage in, what percentage would be this guy? 20% of that guy contributes, and so forth. The same idea with the average. Stay with me now. This is kind of gross. So to get the standard deviation, I could do all this frickin' work and then add that shit up. And again, do you see how it's the same formula again? What was the formula before for the variance? It was sum of x minus the mean squared divided by n. Well, what's on the bottom of that stupid dude? N. Same formula. Sweet. Maybe. Now, so guys are like, just barely with you. All right, so this is where some algebra comes in. Because that formula is kind of disgusting. It's got a lot of parts to it. Is there any way, Jeff, that you can just have one more column only and get what we need? Yes. If I look at this guy, just stare at that. Just look. Now look at it with your algebra brains in, all right? And so you guys, I burned that thing. All right, come on. If you saw this in algebra, now you wouldn't normally see that letter, but I don't give a shit. It's just a number. It's just a letter, right? What would you have to do to simplify that? Yes. Right? So let's just focus on this dude for a minute. Let me pull him out of there. And to FOIL it, you'd have to write it twice. Now just take a minute and do that for me. FOIL that out. What are we doing right now? We're developing a better formula. You're never going to have to do what we're doing right now again. But you're going to help me put a better formula together. I love you. You're like, I don't trust you, man. It's not going to be better. I don't blame you too much. You guys remember how to FOIL? I tell some of my students, when I teach this in my algebra class, I say, I wish they never came up with stupid flippin' FOIL. It's bullshit. FOIL is bullshit. Anytime in math or anywhere we make a mnemonic device, like PEMDAS and so forth, PEMDAS makes some sense. FOIL makes zero frickin' sense. It makes it seem like it's harder than it really is. But how do I FOIL? I really just distribute each of those. I don't have one thing to distribute, I got two. So I distribute the x. What do you get?
X squared.
X squared minus?
X of x.
Who to what?
X.
I love you guys. X mu. And then you distribute the negative mu, right? What do you get here?
Negative mu x
Negative mu x.
times mu squared.
I like it. Oh, I love some. Again, what did I say just a minute ago? You'll never have to do this again. What are we doing right now? What are we doing, Jeff? What are we doing? We're making a better formula. Using the most useful tool in all mathematics, algebra. I'm not the only person that feels that way, which means I'd be the only person that's right. Any like terms in this thing? Stuck up asshole? No, I'm just right. Are these like terms? Hell yeah. They both have an x and a mu. So how many things do I have that have an x and a mu? 2. Negative 2. All right. Let me bring it over here. I love you guys so much because right now you're like, how much of this do I have to worry about? 0 in the long term. All of it right now. All right. So let me write this again. So we got this. And we worked it to be this so far. All right. Right? Just plugging in. Did we just FOIL this and get this? So I replaced this with this. Bam, that's all I did, right? We did that work on the side, we can throw it back in. I think the building over is lifting off. Sorry. Now, in the interest of time, and if you are curious to see all the steps, you can always come to my office. I'm not going to show us all the steps, and some of you guys are appreciative. But if you work this out, let me see if you can see the first piece. What does this want to do? What does it want to do? Distribute, right? Isn't that times? So what would the first piece of that be? X squared p of x. Now, believe it or not, and again, I hope that at least one person is curious. If you do all the rest of this shit and you work and work and work, you get this. Everything else that you get boils down to that. Everything else you get from this becomes this. And if you don't believe me, I'll show you. I'm just not going to do it in class. It's got some extra shit we don't have to worry about in here, but you should be curious. Just not going to do it up here. At least you can see the first piece, right? Bam! Now what is... Now, okay, so if you've tuned me out up until now, come back. Because now this is what we need to know. This is now our formula for variance. And I know exactly what you're thinking. That is worse, Jeff. Thank you for all this work to make it worse. You're welcome. But what does this mean? Now watch. Now all I need now is one more stupid column. Do you guys see that? I just need one more column. What do I need for this formula? I need to add up a bunch of what's? X squared p of x's. So I just need one more column. So you could either square these and multiply by this, right? Then to say the x is squared times p of x. What does this say it needs? X squared, okay, I can square these numbers, times p of x, times this. Or you could be a complete geek with Jeff and say, okay, what's x times x p of x? X squared p of x. 1 times 0.2 is 0.2. What is x times x p of x? X squared p of x. Bam! So what's 2 times 0.8?
0.6.
No, 1.6. 2 times 8 is 16, so 2 times 0.8 is 1.6. You move the decimal back one place. What's 3 times 0.3? Thank you. And 4 times 1.2? 4.8. You know, job, man. So I'd have to ask you a question. And all right, that's all I need is one more column. It's relatively quick to get, and then I throw it in the formula to get the variance. So here I get, if I add these up, 1.8, 2.7, 7.5. Is that what it is? I might have done that too quickly. Let's see if you get it the other way. 5.7, 7. Yeah, 7.5. You guys with me? This should feel familiar. We have a different formula, but the idea is make a column of stuff I gotta add, and then amazingly enough, I add them. So where does 7.5 go? Here. I'll tell you where it goes. Where's 7.5 go?
First part of it?
Yeah, this is 7.5. So the variance is 7.5 minus what squared? We got the mean already, right? 2.5. So minus 2.5. And the most commonly forgotten dude is to square that poor little dude. I'm sorry, we put it up here. Those of you in the back of the house. So this is 7.5. The mean was 2.5 squared. Somebody help me out. What do you get for that? I think it's 1.25.
1.25.
Ha! Sorry, celebrate small victories. And then of course that is the what? Variance, because I haven't done what yet? Square rooted. So what do you give me? Square root that business? Do that one, Jeff. I don't want to. Maybe 1.1 something. Like 1.15 is my guess. I don't know.
1.18.
What is it? Sorry?
1.118.
1.118. Yes.
So you know standard deviation for like a sample is like n minus 1 of the denominator?
True. But this is where I'm always going to assume it's a population that I'm working with. Notice there's a little more to this whole story, but notice the most basic reason I have to assume that is, see how I'm always multiplying by p of x? Right? What's on the bottom of it? What's on the bottom of any probability? N. So that's got to be the standard deviation of the population then, because it's not divided by n minus 1 like you're saying, right?
So
Okay.
why do we, because for the formula that we created just now, we purposely only put n. How do we know to just put n and then not n minus 1?
We don't have to put n. It's built in for us. Yeah. I like it. Maybe. So, not surprisingly, got a little worksheet. One side is an entire problem worked out, and the other side is what I need you to do right now. How much time we got? Tons of time. It's too bad for you.